Einstein's Relativity, the Special Theory and the General Theory. Chapter 5, The Special Principle of Relativity. New Modern Translation 2024. Albert Einstein and Harry Yoon, Translator. Introduction, Chapter 5. Throughout the history of physics for the past few thousand years, there were many occasions in which there were competing theories that attempted to explain the same natural phenomena in different ways. Such was the case with respect to the model of our universe at the turn of the 17th century in Europe. There were two major competing theories, namely the heliocentric and geocentric world theories, and it wasn't entirely clear which theory was correct. Most people at the time believed that the Earth was at the center of the universe, and the Sun, stars, and all other planets rotated around the Earth. This geocentric model of the world was originally created and perfected by the ancient Greek philosophers such as Aristotle and Ptolemy. This is now known as the Ptolemaic theory. In the mid-16th century, Nicolaus Copernicus proposed an alternative model in a book on the revolutions of the heavenly spheres, in which he put the Sun at the center of the universe, and he postulated that all planets, including the Earth, rotated around the Sun. This heliocentric model was a truly radical idea, not because the Sun was placed at the center, but because the Earth was not at the center of the universe. Copernicus, who was an ordained Catholic priest, was fully aware of its potential for controversy. The book was arranged to be published right before his death. For the following few decades after Copernicus' death, the resolution of these two competing theories, the traditional Ptolemaic theory and Copernicus' new moving Earth theory, became one of the most important scientific questions. Galileo was one of those people who were interested in this problem. Galileo was a late bloomer. Although he had been working in the field of physics as a lecturer-tutor, he hadn't published any books, which was considered an important achievement of the intellectuals at the time. When he heard about the new invention called telescope, around 1608 to 1609, he immediately got interested and started making one for himself. His new telescope had a resolution high enough, -9x, that he could see certain details of heavenly bodies. He saw mountains on the moon, which was against Aristotle's cosmology in which heavenly bodies were all perfect and pure. He saw black spots on the surface of the Sun, and even observed that the Sun was slowly spinning. He discovered the 4 big moons of Jupiter, now called Galileo's moons, and again he saw them rotating around Jupiter. They were revolutionary discoveries that no other human beings before him had ever seen. Galileo published his findings in his first book, The Starry Messenger, in 1610. He was some 45 to 46 years old. Seeing was believing. Based on his observations, he no longer had any doubt that the Earth was just one of the Sun's 6 planets, and they all rotated around the Sun. Galileo became a vocal proponent of Copernicus' heliocentric theory. However, he soon realized that it was another matter to convince other people. One of the major objections to the Copernican theory was, if the Earth is rotating around the Sun at a high speed, how can we, who live on the surface of the Earth, not feel its motion? Anybody who had been on moving vehicles like a horse carriage surely knew that they could easily tell that they were moving. How could you not know? The moving Earth theory of Copernicus was, to the vast majority of people, a complete nonsense. Galileo now had a mission. How can we explain this apparent paradox that we did not notice the motion of the Earth, which was rapidly moving in space? It took Galileo many years, but being a persistent person, just like Einstein, he finally came up with a solution. He published this result in a book titled Dialogue Concerning the Two Chief World Systems in 1632. This is now called the Galilean Principle of Relativity, which is the basis of Einstein's special principle of relativity, which is the topic of this chapter, Chapter 5. Chapter 5. The Special Principle of Relativity. In order to be able to present our ideas as clearly as possible, let us once again use our train as an example, which is moving at a steady pace on a straight and level track. We call such a rectilinear motion a uniform translation. It is a uniform motion because the train has a constant speed and direction, and it is a pure translational motion because, although the train changes its position relative to the embankment on a straight path, it does not make any rotations. Imagine now a raven flying through the air. Let us suppose that, when observed from the railroad embankment, the raven flies with a constant speed in a straight line and without rotation. The motion of the raven can thus be also characterized as a uniform translational motion with respect to the embankment, or with respect to an inertial reference frame attached to the embankment. If the flying raven is now observed from the point of view of the uniformly moving train, or an inertial frame of reference attached to the train, then the motion of the raven will appear, in general, as a different motion along a different trajectory, e.g., with a different speed and in a different direction to an observer on the train. Nevertheless, one can easily convince oneself that the motion of the raven will still appear as a uniform translational motion even to an observer on the train. That is to say, the raven will also appear to be flying uniformly at a constant speed in a straight line, without spinning, to an observer moving with the train whose motion is a uniform translation. Stated in a more abstract manner, if a body of mass m is in a uniform translational motion with respect to a reference frame k, then it will also be in a uniform translational motion relative to a second reference frame k', provided that k' is in a uniform translational motion with respect to the first reference frame k. In view of the explanations given in the preceding chapter, with regards to the definition of the inertial frame, it then follows. If K is an inertial reference frame, then every other reference frame K' is an inertial reference frame if it is in a state of uniform translation relative to K. The mechanical laws of Galileo and Newton hold with respect to K' exactly in the same way they do with respect to K. We now take this generalization one step further and rephrase the statement even more broadly as follows. If K' is a reference frame which is in a uniform motion, without rotation, relative to another reference frame K, then physical processes with respect to K' follow exactly the same general laws as with respect to K. We call this statement the principle of relativity, or more specifically, the special principle of relativity. As long as one was absolutely certain that all natural phenomena could be understood within the framework of classical mechanics, one could not doubt the validity of this principle of relativity. With the more recent development of electrodynamics and optics, however, it became more and more evident that classical mechanics was not sufficient as a foundation for the physical description of all natural phenomena. This, in turn, made some people raise questions regarding the validity of the principle of relativity itself. And it did not seem completely out of the realm of possibility that the principle of relativity might indeed turn out to be not universally valid. At the end of the day, however, there have been two general arguments which, from the beginning, seem to speak strongly in favor of the validity of the special principle of relativity. First of all, even though classical mechanics does not provide a sufficiently broad basis for the theoretical representation of all physical phenomena, it nevertheless has a very important element of truth in that it has been so successful in providing the description of the actual motions of the celestial bodies with such an admirable accuracy. We must therefore take it as an indisputable fact that the principle of relativity applies with great precision in the field of mechanics. It is not a priori very likely, then, that a principle of such great generality, which applies with such precision in one domain of phenomena, would fail in relation to another domain of phenomena. The second general argument in favor of the principle of relativity, which we will revisit later, goes as follows. First, if the special principle of relativity does not apply, then the inertial reference frames K, K', K double prime, etc., which are moving uniformly without rotation relative to each other, will not be equivalent for the description of natural phenomena. If this were the case, then we would be led to the only possible logical conclusion that there must exist one special reference frame K0, with a certain particular state of motion, among all possible inertial reference frames, relative to which the laws of nature could be formulated in the simplest and most natural way. We would then be justified in calling this special reference frame stationary, because of its advantages for the description of natural phenomena, while calling all other inertial reference frames K non-stationary, or moving, because they are in motion relative to this special inertial reference frame. If, for instance, our railroad embankment were the stationary inertial reference frame K naught, then our railroad car or the train would be a non-stationary inertial reference frame K. Relative to K, then, less simple laws of physics would hold than relative to K naught. This lower level of simplicity would be due to the fact that the train K would be in motion with respect to the special frame K naught, which we have designated as the stationary frame of reference, and in which the laws of nature have the simplest form, by definition, among all other inertial frames of reference. In particular, with regards to the general laws of nature that are formulated in relation to K, it is not unreasonable to assume that the particular speed and direction of the traveling train, with respect to the special stationary frame of reference K naught, would play a role in these laws of nature in some way. One might expect, for example, that the tone of an organ pipe, if its axis were placed parallel to the direction of travel, would be different from the tone if its axis were perpendicular to that direction. Now, because of its orbital motion around the Sun, our Earth can be viewed as a train K, which is traveling with a speed of about 30 kilometers per second, relative to the Sun. It would therefore be expected that, if the principle of relativity were indeed not valid, the direction of the motion of the Earth at any moment would then enter into the general laws of nature. The physical behavior of the terrestrial systems would depend on its spatial orientation in relation to the Earth, and the Earth could not be at rest relative to the hypothetical reference frame K naught throughout the whole year, because of the change in the direction of its orbital motion in the course of the year. Hence, we would expect that the physical systems on the Earth would exhibit different behaviors, depending on its orientation or on the time of the year. However, neither such an anisotropy of the physical systems on the Earth, nor any other discernible physical non-equivalence of different directions, has ever been found, despite the most careful observations made in recent years. This is indeed a strong argument in favor of the special principle of relativity. Translator's notes. In this chapter, Einstein introduces the special principle of relativity through a series of generalizations, starting from the Galilean principle of relativity. The special theory of relativity is a simple consequence of the special principle of relativity. Everything in special relativity, literally everything, follows from this seemingly obvious principle. In physics, words like law and principle are more or less interchangeably used. But a principle in particular refers to sort of a hypothesis which is supposed to be true, e.g., because no counterexamples have been ever found, but which cannot be derived from any lower level or more fundamental laws or principles. In the second half of the chapter, Einstein provides a couple of reasons why the special principle of relativity must be true. These are like circumstantial evidences and not proofs. If you don't completely follow the logic, you can ignore them and simply accept the principle of relativity as indisputably true. Nothing is absolutely true in physics, but if there is one thing that is close to the absolute truth, then it is special relativity. A quick summary. Uniform translation is a rectilinear motion at a constant speed without rotation. A uniform translational motion of a body, when the body is viewed from another body which is in a uniform translational motion, is also a uniform translational motion. From this follows that if a reference frame K' is in a state of uniform translation relative to an inertial reference frame IRF K, then K' is also an IRF. The Galilean principle of relativity can then be stated as follows. The laws of classical mechanics that hold with respect to one IRF hold exactly in the same way with respect to another IRF. We generalize it as follows, which we call the special principle of relativity, or simply the principle of relativity. If K' is a reference frame which is in a uniform translational motion relative to another reference frame K, then physical processes with respect to K' follow exactly the same general laws as with respect to K. But this principle, generalized beyond mechanics, seems to be in conflict with electrodynamics and optics. Does that mean that we will have to abandon the principle of relativity? Ultimately, however, there are two general facts that speak strongly in favor of the validity of the principle of relativity. First, this principle works so well in one domain of physics, so it is not unreasonable to expect it to work well likewise in other domains as well. And second, if the principle of relativity is not valid, then there must exist a special or preferred frame of reference, in which the laws of nature are particularly simple. But despite much effort, no such preferred frame of reference has been found. Degrees of freedom. As an idealization of real-world objects, Newton introduced the concepts of point particles and rigid bodies, among others. A point particle has a mass but does not have a volume. That is, it does not occupy space. A point mass has 3 degrees of freedom, in that its position can be specified with 3 Cartesian coordinates. A rigid body, on the other hand, has 6 degrees of freedom, to indicate its location, 3 positional degrees of freedom, as well as its orientation, 3 rotational degrees of freedom. Although it's not always explicitly stated, since the frame of reference is an abstraction of rigid body, frames of reference have the same 6 degrees of freedom as well. In the first part of this book, however, we pretty much ignore the rotational degrees of freedom, and we only consider uniform translational motions, that is, the uniform motions without rotations. Uniform translational motions. In the beginning of this chapter, Einstein makes the following claim. If a body of mass m is in a uniform motion with respect to a reference frame K, then it will also be in a uniform motion relative to a second reference frame K', provided that K' is in a uniform motion with respect to the first reference frame K. This seems rather intuitive, but it can also be easily proven using linear equations, e.g., by treating time t as just another coordinate. This is explained in Appendix C, again ignoring the rotational motions. Inertial reference frames. In the previous chapter, inertial frames of reference were defined using the Galilean law of inertia. That is, an inertial frame of reference is a frame of reference relative to which the law of inertia holds. Now, based on the above proposition regarding uniform translational motions, we can easily infer the following, as Einstein states. If K is an inertial reference frame, IRF, then every other reference frame K' is an IRF if it is in a state of uniform translation relative to K. Note that according to this statement, all IRFs form an equivalence class, mathematically speaking, with respect to the relations of uniform translational motions relative to each other. This means that, among other things, a reference frame should be either IRF or non-IRF, but not both. And hence, this statement can also be used as a definition of IRF. Inertial reference frames can also be defined in terms of acceleration, or lack thereof. A uniform translational motion, with respect to an IRF, is a motion without acceleration. Therefore, an IRF is, or can be defined to be, a reference frame in which its own acceleration is 0. Or in other words, an IRF is a reference frame which is, when it itself is viewed as a rigid body, in an inertial motion, i.e., a uniform translational motion, with respect to another IRF. As stated, inertia and the inertial frame of reference, and hence the principle of relativity, are all closely related. The special principle of relativity. The principle of relativity generally refers to the principle that every observer sees the physical laws as the same. There can be variations depending on what we mean by observers and physical laws, etc., and there are indeed a few variations as used in physics. The general principle of relativity is the most general form of the principle, as the name implies, but it is rarely used. In fact, most physicists may not even be familiar with the term. Einstein was the only person who not only invented this idea as a generalization of the special principle of relativity, Chapter 18, but also relied on this principle to create a new theory, namely the general theory of relativity. The term Galilean principle of relativity was retroactively invented, very likely rather recently, because at the turn of the 19th century, the principle of relativity had to be reinterpreted. Now, the Galilean principle is the historical version of the relativity principle, which only applies to the classical mechanics of Galileo and Newton, whereas the Einsteinian or special principle of relativity is the newer version of the relativity principle, which is supposed to apply to all physics, including electrodynamics. Technically, there are some other differences in the way these two terms are used in modern physics. This will be further discussed in Appendix A. Here's the Galilean principle of relativity, slightly condensed. If K and K' are inertial reference frames, then the laws of classical mechanics hold exactly in the same way, both with respect to K and K'. Here's the special principle of relativity, again slightly paraphrased. If K and K' are reference frames which are in a uniform translational motion relative to each other, then physical processes follow exactly the same general laws with respect to both K and K'. The primary difference between these two is the laws of classical mechanics versus the general laws of physics. When we simply say the principle of relativity, we generally refer to the special principle. Note that there is no explicit mention of the word relativity in either version of the principle of relativity. As we mentioned previously, Appendix A of Chapter 4, the use of the word relativity turned out to be a somewhat unfortunate choice. The more common meaning of the word relative, as in hot and cold are relative, has little to do with the meaning of this word in relativity, as in the relativity of simultaneity, Chapter 9. Ironically, the special principle of relativity, as stated above, is really about the non-relativity part of nature, e.g., across different inertial observers. That is, the principle states that all laws of physics should be the same or non-relative with respect to all inertial frames of reference. It is somewhat paradoxical that we tend to emphasize the relative part of nature when the more fundamental truth is the fact that we, all of us, see the world in accordance with the laws of physics in exactly the same way. The principle of relativity can also be understood from the perspective of empiricism. For instance, if you cannot distinguish the moving and stationary states, e.g., using any experimental methods, then these two states should be considered equivalent for the purposes of describing physics. This is a very reasonable assumption. If this principle did not hold, then the world that we live in would appear rather capricious and arbitrary. Incidentally, Einstein was guided by various philosophical principles while working on the theory of relativity as well as quantum mechanics. As stated a few times already, everything in the special theory of relativity follows from the special principle of relativity, that is, through a straightforward deductive method. Einstein categorizes theories in physics into two kinds: constructive theories and principle-based theories. For example, in his article, What is the Theory of Relativity? 1919. There are pros and cons with either kind of theories, but the principle-based theory is generally more coherent, and it is harder to invalidate only certain parts of the theory without destroying the whole theory. The special theory and the general theory of relativity are both principle-based theories, but this characteristic is more pronounced in the case of special relativity. Much of the explanatory and predictive power of the special theory of relativity come from the fact that it is based on the so far undisputed principle, namely, the special principle of relativity, Appendix D. The stationary frame of reference. Although we just used the word straightforward, the development of the special theory of relativity was anything but straightforward. As a matter of fact, special relativity was born out of this serious conflict between the Galilean principle of relativity and the then relatively new electrodynamics of Maxwell, among other things, as Einstein explains in this chapter. This is further discussed in Chapter 7. With respect to this conflict, Einstein sides with the principle of relativity, ultimately modified as the special principle, and he gives two general reasons in this book. First, although Einstein admits that the principle of relativity is not an absolute law, he conjectures that this principle will hold true in all domains of physics as well, since it works so well in the realm of classical mechanics. Obviously, this is a speculation, or an unproven extrapolation. But Einstein believes it to be true, which seems reasonable in the absence of any evidence to the contrary. In fact, all known fundamental laws of physics are consistent with the special principle of relativity to this day, including the celebrated Standard Model of particle physics and whatnot. The second argument in favor of the principle of relativity is more interesting. If the special principle of relativity does not hold in general, then that means that not every inertial frame of reference will be all equivalent to each other in terms of the laws of nature. Furthermore, the laws of nature in general will have a dependency on the motion of the reference frame, e.g., its speed and direction, and hence they will be presumably more complicated. It then follows that there should exist one preferred frame of reference, in which the laws of nature are particularly simple. But despite much effort, neither the dependency of the physical laws on the motion of the reference frame nor any special preferred frame of reference has been found. Hence, as Einstein concludes in the book, this should be viewed as a strong evidence that supports the principle of relativity. One thing to note is the use of the word stationary in this argument. Einstein also used this word in his first paper on special relativity, on the electrodynamics of moving bodies, 1905, which caused and still does so much confusion. The word stationary in this context is just a somewhat arbitrary label, and it has little to do with the rest state, as in something is stationary with respect to the absolute space. The existence of a certain preferred frame of reference was a topic of debate for many years before and after the publication of Special Relativity, and it is still debated, at least in philosophy. Moreover, since the discovery of the cosmic microwave background, CMB, we now know that there does exist a special frame in this universe. But it is still not clear what this entails in terms of physics. This is one of the biggest open questions in modern physics. The ether. In the initial development of the special theory of relativity, the idea of ether did not play a significant role, as we will see in the following few chapters of this book, as it follows the historical development, cf. Einstein's preface. In the aforementioned paper, on the electrodynamics of moving bodies, Einstein merely uses the word unnecessary or superfluous to refer to the ether. Interestingly, for the following few years, Einstein gradually put more and more focus on the ether. In fact, he came to the opinion that any physical theory which presupposed the existence of some kind of stationary ether could not be correct. For one thing, the ether was not consistent with the special principle of relativity. Then, in the following few years leading up to the development of his general theory of relativity, GR, he started using a concept that was reminiscent of the ether. He initially called it the ether of GR. This is what we now call spacetime in the context of GR. There are many differences between the media generally called ether, as the term was used by Maxwell and Lorentz, etc., and the spacetime of GR. But regardless of their differences in detail, what's important to note here is that Einstein initially thought that space, in the sense of Newton, did not exist, a la Leibniz, etc., while developing special relativity. But while working on GR, he had to reintroduce some kind of space, or spacetime. The spacetime of GR is really a field, just like electromagnetic field. Is there another more foundational space and/or time, on which the spacetime field resides? Nobody knows. In modern physics, spacetime is really the final frontier. We have some fragmented knowledge about certain properties of, or related to, spacetime, in the context of GR and QFT, etc., but ultimately nobody knows what spacetime really is. Michelson and Morley's experiment. Most textbooks on special relativity emphasizes the role of ether in the development of the special theory of relativity. Many textbooks, in fact, start with the null result of the Michelson-Morley experiment. As just stated, however, Einstein almost retroactively realized the importance of the idea of the ether. At the time of his initial development of the theory of relativity, in 1905, he wasn't likely aware of the Michelson-Morley experiment. This experiment, and its null result, can be interpreted in a few different ways. But as Einstein explains at the end of this chapter, it is now considered a strong proof of the non-existence of ether. This is further discussed in later chapters. What's next? In the next 2 chapters, Einstein describes the situation in physics at the turn of the 19th century, which might be regarded as the crisis of the old physics due to the conflict of classical mechanics and electrodynamics and optics. In particular, in Chapter 6, he explains the apparent conflict between the classical law of addition of velocities and the law of the constant speed of the propagation of light. Then, in Chapter 7, he explains in some more detail how the principle of relativity appeared to be in an irreconcilable conflict with the law of the constant speed of light, before the advent of special relativity. Chapter 6, Addition of velocities in classical mechanics. Chapter 7, The law of constant speed of light and the principle of relativity.